Good morning, ladies and gentlemen. Good morning. I am Colonel Basha, Base Commander. On behalf of my command, Turkish General Staff, I would like to welcome all of you, and I hope you all are welcome with your accommodation. You don't have any problem with your transportation, etc. I'm quite sure that the conference related, the issue related to the conference are okay. On the other side, if you have any concern, problem with your daily life, please let me know. Me or my colleagues, they are here, are very happy, will be very happy to solve if you have any problem. Before giving the floor to Dr. Tanya, any question for any problem? Yes. Enjoy your way. Dr. Floor is yours.
Well, I would like to welcome you to TÜBİTAK İlteren building, which we're proud to share with the Turkish General Staff. We will be here for 2 days for this activity, NATO SET-157 Lecture series. We are happy to host this activity, and I see that everybody in this audience is somewhat related to the defense technologies, and I believe the presentations will definitely contribute to your future work. Due to much interest, we now have 2 conference rooms. The second room will be connected to this one via video conferencing, and I hope you not only benefit from the activity but also have fun as well during these 2 days. Please let us know. My staff will be around. Just let us know if we can help. And I would like to use this opportunity to thank our distinguished lecturers and also Dr. Murat Efe for their time and effort. And thank you.
Just a few points. First of all, I would like to welcome you all, and I think we're all very honored, and it's a big privilege to have such a distinguished selection of people here. And I think that over the 2 days you will be quite pleased what you will be you're hearing, and there'll be, I think, lots of discussions out in the foyer as well. And we've got 2 different conference rooms, as Dr. Tanya said, and if the people in that room would like to come here during the breaks, they can always talk to our lecturers here. I think a few thank yous are due, and I'd like to thank NATO Research and Technology Agency first for providing this opportunity, for getting together these guys here and helping them travel around to share their knowledge with us. I would like to thank the lecturers actually making the effort and time to travel around and come to Turkey as well. I would like to thank Dr. Tanya here, because basically what you're experiencing here is without his help and effort, this wouldn't be happening. And we're really sorry about the attendance. I would like to thank you all, because I was expecting there would be a big interest on this subject, but I wasn't expecting this. So we had to divide the people in 2 conference rooms, and hopefully, this will be all acceptable by you. There's one thing: you will find your questionnaires in your bags, in your packs, and if you might have received them through email from NATO as well. So if you'd like to fill them out, you can hand them over to me, or if you have the soft copies, you can actually fill them out and send directly back to the NATO representative. And one more thing, these badges, they're not to take home. They've got magnetic cards in, so if you'd like to return them on your way out, you can, while you're collecting your own badges, that'd be great. So I think there's not much to talk about now, and we would like our lectures to start. Thank you again for coming.
Morning also from me. It's very impressive to be here, to see such a huge audience. Normally, as Murato has asked me when he agreed to organize it, he says, how many people you could expect? And I said, the best what I had this time was about 50 to 60 people. And now he outnumbered every location with over 100. So very good promotion, very good place, and Ankara, what I have seen until now, is also very nice. So I'm very happy to be here. This is, I think, the same with the other lecturers. And also I'm realizing it's like German, very wonderful schedule, everything is printed out, and unfortunately I behave a little bit non-German. I have to adapt it on a special need. So we have a new program. We will stick together in the time, hopefully. And what I should mention, if you stay the whole 2 days, you will all receive the lectures. So another thing, if you have questions, don't hesitate. Ask them during the presentation. Ask them after the presentation. Take the time during the coffee break. So no problem. Normally there's a roundtable discussion, as it will be the case in the last lecture locations. We have no round table, but we have a discussion always after the presentation. So, and I think now it's time to wish you very interesting lectures, and hopefully you will get new ideas. It's, I think, a good possibility to meet colleagues, to get in touch with each other, and that's for my point. And also I would thank Murata for the effort he has already put into to organize this event, and also NATO who made this event available due to funding our travel from one to another location. So, is there any official for the NATO presentation?
I think Stefano will be the
Stefano. Okay, the first presentation now will be, as mentioned...
You sound very disappointed.
It's a short overview of NATO, and especially focus on the RTO organization who is funding this presentation, lecture series. The reason why Stefano will give this talk, as he has nearly or 8-year experience working at the NATO Undersea Research Center in La Spezia, left 2010. And as you are the experienced guy, we have now the word.
Okay. Well, first of all, good morning to all of you. So as Matthias mentioned, I'm going to just present a few slides on behalf of Elio Vincitorio, who's the SET representative in NATO. And so these are his slides, but hopefully I can do justice to them. Let me just mention that we do have here Lieutenant Colonel Alp Alper, who is sitting right in the first row. He's the Turkish member of the SET panel. So if I make any mistakes, he will correct me here. So what can I tell you about the RTO? So the most important thing to understand is I found it very confusing for a very long time. So there's the RTA. The RTA is the NATO Research and Technology Agency, which is, maybe about 30 people. It's a small center in Paris, and they don't do any of the research themselves, but they coordinate all of the activities of the larger RTO. So, for example, this event now sits as part of the RTO. So we don't work directly for NATO, but during the time of this lecture series, we're part of the RTO. So the RTO is quite large, because if you're involved with any of the activities that the RTA coordinates, you're part of the RTO. So let's see. The RTO is focused on technological developments in defense and security. And so this gives you a sort of an organizational look of. So one of the nice things about the RTO is that it provides a link between military activities and more civilian research activities within NATO. So for instance, NATO has two research centers. One is in The Hague, NC3A. The other is the NATO Undersea Research Center in La Spezia, in Italy. So NC3A does mostly command and control activities, while NERC, by its name, you can see, is more focused on undersea surveillance and increasingly maritime surface surveillance as well. So I think the next slide tells us a little bit more about what the RTO is composed of. So as I mentioned, there's the agency based in Paris. There's a consultative board, which includes a number of individuals from many of the nations. For example, the director of NERC, the center where I used to work, is part of the Research and Technology Board. And then there are a number of technical activities, or technical panels. What we're doing here today is something that is sitting under the SET panel. So you can see here, by the way, all of these slides, these introductory slides, but more importantly, the lectures, will be made available to you. You'll be getting an electronic link that Matthias will give you at the end of the day tomorrow. So don't worry about writing things. You can take notes, but don't worry about things that you may not have time to write, because you'll receive all this material. And I think most of what I'm mentioning here, in fact, is on the RTA website. But at any rate, so what we're doing now fits under the SET panel. You can see some of the technical areas that the RTO covers. So as SET panel, as you can see by its name, is focused on things like electronic warfare, communications, intelligence, surveillance, and reconnaissance. So both the hardware side as well as the signal processing and the downstream information extraction, which is what we'll be talking about the next couple of days. Now, within the SET, but also within the other technical areas, there are various types of activities that exist within the RTO. So what we're doing now is a lecture series, but as you can see, there are various types of conferences of varying sizes. There are also task groups, and the main message that I would have for you here is that if you have an idea, if you'd like to organize a symposium, a smaller workshop, if you'd like to be involved in a task group with researchers in your field, in some of the other NATO nations, if you have an idea for a lecture series on a different topic, you can submit a proposal, in this case to the SET panel. If it would fit under another area, you would submit it to another panel. And the SET panel meets, I believe, twice a year and reviews proposals and chooses some things to fund. So keep this in mind as something that a vehicle to obtain some funding, but more importantly, to engage researchers from across NATO. As you see, the RTO is quite large because it includes, as I mentioned, part-time participation from people from many organizations in government, industry, and this is just a quick snapshot of the number of activities. The nice thing to note is that the number of funded activities is staying steady and actually slightly increasing, which is not always the case with activities within NATO. For instance, the funding for the NATO Undersea Research Center is increasingly difficult to maintain because of NATO activities, mostly ground activities that are going on these days. So that makes it difficult to maintain funding for undersea research. This is just a random snapshot, I think, of some current activities, but you can find more on the website. And I think that's it. So are there any questions about, and so I guess I'll end with a thank you to the RTA for agreeing to fund this activity, which actually started last year. We had 4 stops last year, and then we were funded for an extension to this year, and this is our 4th stop this year. So thank you to the RTA, and any questions? Don't ask me difficult questions about NATO, because it's very difficult. Okay, thank you.
We will start with the first presentation. This one. So, you will hear several presentations, not only this day, also tomorrow. The main focus of the presentation will be on combining software sensor data and fuse them, extract tracks, and detect targets or monitor targets, how they behave over the time. And my part is to see more in how one can build such sensor networks so one can do the data fusion with them. Therefore, my first presentation is just called Multisensor Systems with Multiplicity House, and you will hopefully see that if you spend a little bit more sensors in your network, you will get you benefit from it. Therefore, I will start with a short motivation, and then we'll go into which type of sensor networks are possible. You can think of using a single type or monotype sensor, or use different sensors, for instance, optical, chemical sensors, and fuse the data, and I call it a multi-type sensor this time. As I'm working on radar, I will also focus a little bit more on a radar network, as I will show that one can get a lot of using or employing a single type sensor, especially a radar. And therefore I will explain some properties of a multistatic radar network consisting only, again, radar. If you're working like Stefano on a sonar system, you will probably replace the word radar or the sensor nodes with sonar systems. And finally, I will show you some examples of existing multistatic systems one can see which are already working or in the development phase. So, why should one use a multi-sensor system? One reason is that the single sensor is beginning to reach the limit. If you think of a radar sensor, you are not able to increase the power anymore to increase the range. You are limited, for instance, using semiconductors by a couple of kilowatts and using tubes to several megawatts, but not beyond. Your tube will blow up if you want some more power to get further away. Another possibility is to increase your antenna size. So if you remember the radar equation, you have the possibility to do it with the antenna size, but also there you will get some problems. In Germany, near where I'm working, there's a 100-meter dish. The Effelsberg is a radio telescope, and I think it's very impressive to see it, but it will not go beyond this place. So there must be a different approach to overcome these limits. Another point, especially from the military view, is that the monostatic systems is vulnerable against physical and electromagnetic jamming. And also, if a stealth object is approaching on monostatic systems, you will not see it, as the design was so optimized that it shows a minimum radar cross-section for a monostatic system. But this is not the case for a multistatic system. You always have the possibility to see the target, as there is much higher reflection in a different direction. Again, if you're designing a monostatic or a stealth object, you always keep in mind you are using the enemy who not want to detect, who should not detect the target, is using a monostatic system. So the design is always having monostatic, that the energy is spread over a broader angle range than for a monostatic system. Also, using several sensors in your networks improves dramatically your sensitivity of the network. This helps to recognize and to detect your target, and also you are able to determine the position of your target with a higher accuracy. It's possible to overcome the counter-stealth problem, and also possible to employ new processing concepts like multiply input, multiply output systems. And again, a multistatic sensor network shows less vulnerability against electronic and physical attacks, and improves information context of the area where you are looking into it. Multisensor system offers new possibilities for detecting, tracking, and classification of targets. And one can think of this, the system design has now the possibility that the target is located inside the system. Means, for instance, you have a target in the center and lots of radar nodes are surrounding it. You will, in my second presentation, I will go into it, and one can see that this is a very nice constellation to detect a target and classify it. And hence, this new design, which is not very common to have so-called target inside the system, leads to a radical form for processing, and also one has to consider a near-field operation. Now, there are many possibilities to use or to design a multisensor network, and also one has to think that you can build it up using different sensors, and this will definitely help to characterize and classify your targets. If you see your target with an optical system, you will see it with a, for instance, chemical system, you will see it with a radar system. You get always a different type of information from the target. You can more decide, is it an enemy, or is it friend, or is it a tank? So that will definitely help to classify it. Also, it's possible and very useful to have these sensors on the same place, so you have less problems to fuse the data and to extract the information from it. And on a central processing stage, there's a possibility that then only the tracks from a target or the detections will be fused. Using a single type sensor, thinking of, as I'm always working with radar, I proposed using radar. So If you're using a radar network, you are able to have a higher resolution where's your target. You are able to determine the parameters with a higher confidence, as you are able to do joint estimation. You are able to realize bistatic systems. That means you have a transmitter in one place and a receiver on a total different place, which will improve your interference and jamming systems, and also you are able to deal better with the fading effects. Also, it's possible to use a decentralized processing. Means that each receiver node extracts already tracks, and then decentralized should be tracks, and then the fusion. But also you can think of that all information coherently will be forwarded via a communication link to a central processing stage, and then coherent processing over all nodes can take place. One example for a multi-type sensor network, I have stolen shamelessly from Stefano's presentation. Then you will get more information. Here, information from an AES tracks, which ships are always transmit, fused with ship-based radar tracks and satellite imagery-based chip detections are fused to receive a single plot of the view. This will definitely enhance the possibility to detect the target. Not always the ship is transmitting his AES information, but if you're using a second source, for instance, radar, you are able to detect it. And if you again fuse this information with the satellite imagery, you have also the surrounding of it and see even smaller, maybe smaller ships there. So, in the sum up, you will be able, if you're using a multi-type sensor, to detect your target more clearly. You are able to recognize it, to classify it with a higher confidence, but this will not necessarily lead to a higher accuracy where your target is. This can be done, for instance, using a monotype sensor. There you are able to design each node in a way that it's a transmitter or a receiver, or a node can be a transmitter-receive node. And thinking of radar transmitting node, you are able to design the system performance by choosing the correct carrier frequency, the pulse length, what is needed to detect the target, the power of pulse, even the pulse width is possible. You determine if you are designing the transmitter. You can design the pulse repetition frequency and so on. But one can also think of using pattern systems. Means you are using illuminators of opportunities, for instance, television stations or base stations for mobile phones, and so then you are not able to design the systems. You have to live with what is radiated, but you can use it, and no one knows that someone is listening to the in the air. Then we are able to build up a multiply monostatic operation. So each node is a monostatic node, consists of transmit, receive, and you just combine the information of each monostatic system. You can design it by having multiply bistatic constellation, or any combination in between of it. Also, you can think of that all transmitters or receive nodes are using omnidirectional antennas to illuminate the space. which will definitely reduce the energy on the target, so it will only see like noise signals. And on the receiver side, the signals will be collected and will benefit from a coherent signal processing, so we can compute, for instance, a virtual antenna. Also possible to use a distributed system, spreading it over a very huge area, which will make it very attractive to detect targets with a very designed monostatic radar cross-section, and you are able to have a really high angle resolution for localization. Also, multiplicity of sensors supports a higher accuracy of localization, and you should be able to handle also many targets in your system. And a multistatic systems, different bistatic pairs, will also improve your Doppler processing through diversity of looking angles and migration in the problem of low radial velocities, as moving target will never present the same Doppler shift to two different bistatic pairs. This will sum up in that you will be able to reduce the number of elements in the sensor array. For instance, I was working on a project for three-dimensional LAN image system which should contain a virtual antenna array of 1,400 elements approximately, which should fit on the 5 kilogram small airplane. But we were faced with a problem that we are not had the place for all 1,400 elements. We have not the money for these elements, and to overcome this problem, we had chosen a co-located sensor network using only 36 transmit elements and 44 receive elements, and combining these in the right way, we were able to calculate a virtual antenna array consisting of 1,400 elements. So, spending only a little more than 70 elements, in reality we were able to calculate 1,400 elements. So, that's definitely a decrease of sensor elements in the systems, which saves money, which saves weight and power. Now, facing the problem which sensor one should use, one should think sensor should operate independent of any time constraints, should work on nice weather like in Ankara, not so nice weather like in Lancaster with a little bit rain, should work with sandstorms, hopefully not available here in Ankara, and so on. Also, if you're looking into surveillance applications, the sensor should have a working range of several hundred kilometers. That would be very good. And here I think radar and sonar are very ideal sensors for surveillance and reconnaissance applications. If you're working underwater, you will always choose the sonar, otherwise you will hopefully work with radar. Now, radar is not new. Short history, it was invented by Christian Hülsmeyer. You see it here in 1904. Here you see a cartoon taken from his patent. You can guess. It consists of a transmitter path and receiver. And his first experiment was performed near the Cathedral of Cologne on this bridge, the Hohenzollern Bridge. But it was too early. No one was interested in radar. So the idea was again forgotten and rediscovered, unfortunately, during the war. And also during the war, the bistatic system was again reborn. Was based on an idea from a guy called Wächter, working at Telefunken in Germany, and the whole system was called Klein Heidelberg. And it used the chain home radar system from which I was located at the British coast here around as an illuminator of opportunity. And the power of the transmitter was quite high in the starting phase. In the end phase of 1 megawatt, in the early state was nearly 350 kilowatts. The pulse width was not so short as we are now used today. It was only the shortest way 6 microseconds, but it was very good, and especially a bistatic system. You are not knowing that the receiver is there, that one is able to detect or use the systems. It was so successful, the British people were become aware of the system, and they tried to overcome this bistatic system by modulating the transmit form of chain home and modulating the pulse repetition frequency, but Klein Heidelberg still worked perfectly. So it's very easy and very good and efficient. The easy way, the transmitter was transmitting a signal, this radar signal. You always will have direct signal, so Klein Heidelberg has a reference time. Then also Klein Heidelberg will receive an echo from the target, so you have a time difference. With the time difference you have a bistatic range ring, which is an ellipse, and if you know the places where the transmitter and receiver is located, that's the constraints one has to fulfill, you can draw the ellipses, and in the focal points are transmit and receive nodes. They know the time difference, and using an antenna with a high gain, there was also the possibility to determine the bearing angle, so they can nail down the position of the target. Very good. Now radar systems, quite easy. You will have a signal which is transmitted, travels to the target, and will be reflected, travels back, so that you will have time delayed receive. On the receiver side, you will have a time delayed transmit signal and also some noise. And if the target is moving towards the transmit or receive node from one static system, you also have a Doppler shift, which is proportional to the speed of the target and to the center frequency. Finally, you will have such a formula for your received signal. And the target localization for a monostatic system is in the range direction proportional to 1 over the signal bandwidth, and in the cross range is proportional to the antenna beam width and the range, and this is also limited due to the antenna size and will degrade with the range. And in general, the cross-range resolution will be much poorer than the down resolution. To overcome this, one can use a higher gain antenna, may not help, but here one can think of a multistatic system. We can deal with this short cartoon, and we'll try to explain the advantage using a multistatic radar system. You have a single radar, you will get these range fringes where your targets may be located. They are very huge, you are not able to determine where exact your target is. Using a second transmitter or second transmit receive node, same behavior, different rings, no improvement in localization. Now you are able to build up a time synchronization and some data transmission, so the receive station knows what's this is the transmitted signal. You will get again some range rings, this already mentioned ellipses, but they are very broad, so it does not help. Now overlaying all information you are able to obtain from these constellations using two monostatic systems, one bistatic systems, you will see you can determine the position of your target with a very good accuracy. So multistatic system enhances the detection robustness, as you will always, or mainly will be able to detect the target, as we are using different types of view angles, and finally your localization accuracy is enhanced. Bistatic systems, the geometry is very easy, and it's in a general way. If transmit and receive nodes are located on the same place, it's just the monostatic geometry. Again, you have a transmitter, receiver, they are separated by the baseline L. Then you have a distance to your target, which is flying in this direction, for instance, and then the echo will travel the distance from the transmitter, from the target to the receiver. And the bistatic range means RT and RR summed up. A constant will be ellipses, and in the two focal points there will be the transmit and receive nodes. And if a transmitter is lying on the baseline, you will have a big problem, as you are not able to determine where it is. Is it located here or here? And also, if it's going this way, crossing the baseline, you will not see any bistatic Doppler shift. But using a second bistatic pair, that will never occur that a target will have this behavior to two bistatic systems. Now, again, we can say we have these constant range contours, which one also shows an eccentricity and described by the baseline over the bistatic range, and this will go from eccentricity from 0 to 1. The first extreme is that you have a line just between transmit and receive. Then the bistatic range is the same as the baseline, and the other extreme, eccentricity 0, then it's a circle, and you have nearly monostatic behavior. And the hyperbolas depicted here in the diagram, there are the time difference, the difference between RT minus R2 is constant, and they are used for time difference of arrival measurement, which is used in the multilateration. Bistatic radar equation is similar, derived from monostatic case. We have a transmitter which emits power towards the target, and then will be reflected with radar cross section sigma b, and finally will be picked up by the receiver. And you will see here we have also to take into account again the antenna gains pointing towards the targets of the transmit and receive nodes. It's like the monostatic system, except that you have sum up over all transmit-receive pairs in your network. For a monostatic system, you will receive such a signal-to-noise ratio, which is well known, showing the circles. For a bistatic system, you will get this behavior, sometimes also called Cassini ovals, in between the transmitters. It's lying constellation like 8. Another bistatic pair will show such signal-to-noise ratio, and combining these will gain such a signal-to-noise ratio. As already mentioned, bistatic Doppler, it's a little bit different to a monostatic system. We have to take into account that the change of range difference between transmitter and target receiver will go into your Doppler shift. And finally, introducing the bistatic half angle and still missing the angle of the target velocity in respect to the bistatic factor. You can easily calculate the Doppler shift for a given target or bistatic constellation, and you will see that several cases one can see. If the bistatic sector is 0, you have a nearly monostatic case. If the target is lying somewhere in this region between transmitter and receiver, there will be a forward scatter position, and also, and there the Doppler shift will be always 0. If the target is flying parallel to the perpendicular to the bisector, you will also be able to determine any Doppler shift, and in all other cases you can just use this formula to determine how much Doppler shift will occur. Special interest may be, for instance, if the target is flying parallel to the bisector or is perpendicular to the transmit and receive line of sight. Now, there are definitely coordinate distortion effects due to the coordinates in bistatic systems. Targets on the transmit-receive baseline have 0 bistatic range, so will not be really able to determine. Elsewhere, contours of constant bistatic ranges are ellipses, with the transmitter and receiver side as the two focal points. And as you know, the geometry, the bistatic geometry, you are able to correct this distortion. Also, contours of 0 Dopplers are the same ellipses of constant bistatic range, and contours of maximum Dopplers are hyperbola crossing the ellipses orthogonally, and moving targets cannot present 0 Doppler shift to 2 receiver sites simultaneously. So that is very useful, having 1 transmitter and 2 receivers, and then you will always receive a Doppler shift for any given target. Or you can also choose a constellation having 2 receivers and 1 transmitter. And there are also several configurations of transmitter and receivers possible, and azimuth discrimination at both transmitter and receivers is desirable, since otherwise the system is vulnerable to responses from side lobes, which is a big problem. I will go into this problem in further detail in my second presentation. We will have a big problem with the direct signal, which is very huge in comparison to the reflected signal of your target, what you want to know or want to detect. And if you are using a directional receive antenna, it must show then non-uniform rate to observe the same area as the pulse is traveling from the transmitter node into the space, and this is practically not possible using a mechanical system. You have to use an electronic system, for instance a phase area system or a system with a multi-beam antenna, for instance, which can be used or can be designed by a Rodman lens. Those a small number of electronic angled beams or a static set of continuous beams will be required to overcome this, and such a receiver node is unlikely to be either simple or cheap, but because the receiver is passive, it's much less vulnerable to attack. So In other words, on the bistatic system, one has also think a little bit of the multistatic radar cross-section. Here you see a monostatic radar cross-section for a given plane, and the radar cross-section for a bi or multistatic is nearly the same as for the monostatic. Particularly, the bistatic radar cross-section will be compared for non-stealth targets to the same, but and it will be unlikely that the target will have or show the same radar cross-section to different receiver nodes, and furthermore, at large angles, target flinch is dramatically reduced, eliminating this contribution to radar inaccuracies. Now, as I mentioned, stealth targets are designed to have a low monostatic radar cross-section, partly by shaping so the scattered energy is spread over a very huge angle. Hence, the monostatic radar cross-section of the stealth targets may be larger if you choose the right geometry. Looking into this measurement, you will see the radar cross-section for the monostatic case is very low, but if you are able to place here a transmitter and there the receiver in this range, you will receive very huge energy from your target. But also one should mention that this is a more spiky effect with a very short duration, but you can use it to determine that there is a target and use, for instance, another bistatic pair to monitor these flashes. Now, the bistatic radar cross-section is equal to the monostatic radar cross-section, unfortunately reduced by the factor of the half of the bisector angle. In the case that the target is sufficiently smooth, has no shading effect, and also retroreflectors persist, and one can realize in the multistatic radar cross-section that these spheric phenomena, which contributes to the RCS. You have resonance scatterers, forward scatterers, and spectral reflections. And the first and the last phenomena also applies for monostatic systems, but the forward scatter effect applies only for a bistatic system. There's a couple of guys are working on using this forward scattering to determine is there a target and make surveillance radar. Also, if you have the freeness to choose which frequency you are able to transmit, you have to always to think what is your target. Does it fit to the target size? If the frequency means the wavelength is much larger, looking into the wavelength much larger than your object, you will be in the Rayleigh regions where you have with increasing wavelengths to ratio, target ratio, we have an increasing radar cross-section. If you're choosing a wavelength which is much lower than your target dimension, in this case here it's a sphere with a dimension of 8, you will be in the optical range, and in between you will have some resonance effects, so it's also called resonance region, where wave creeps around the sphere, and so you will have interference effects. And also multistatic, you are able to have bistatic radar cross-section, sure, but also your angle of your scattered energy will have a behavior which is lambda over the d means the target width, and you have to optimize the systems looking into the radar cross-section, which is, no, this should be the radar cross-section going up with a frequency, and your beam angle, the bistatic beam angle where you can detect your target decreases, and you have to find an optimum, for instance, for your target. In sum up, third counter-stealth capability has sometimes been described to bistatic radars in general, the ability to detect specular reflections that have purposely been directed away from anticipated monostatic radar threat locations, for example by using tilted surfaces or facets on stealth platforms. The assertion is that carefully selected location of multiple receivers, these off-normal speculars of large amplitude can be detected and tracked or networked together to support some level of engagement. Remember the image from the fighter with a very low monostatic radar cross-section and large bistatic radar cross-section in this direction, which was very small in the angle range where you can detect it. So you will get more flashes of short duration. So it will be peer optimistic to describe that this will be more than a fence alerting system when using these specular reflections from stealth targets. Furthermore, if you are designing a multistatic radar or radar systems, you can think of that again you are using only monostatic systems, you have bistatic nodes in it, or any combination of these modes. You can also design a network using totally incoherent nodes. Every node works on its own. It's just fusing in a time, in a very short time. So an update every second you will get, and you will only be able to fuse the tracks. You are able, in a short-term coherent network, to do some small coherent signal processing, so for instance for pulse compression. And if you have a fully coherent network, you are also able to do Doppler processing from pulse to pulse in the network. Another type of describing a network is you are using co-located or distributed nodes. You have fixed mobile nodes, ground-based, airborne, space-based, or any combination of these as a network. Also, one can think of you have a time separation between each node. Each node is firing with energy, and then you have to wait until the energy has dissipated, and then the next node transmits. You are using frequency separation, so each node uses slightly different setup frequency to transmit its energy. You can use code diversity using ordinal wave codes, so you can distinguish as a receiver which waveform was transmitted for which transmitter, and you have a lot of processing options. Finally, I would show up some existing samples. A lot of work is going on in the past years. Would like to highlight some of them. There's a lot of work going on in Germany, France, Australia, UK, USA, already in China coming up, and some examples from my work, from my colleagues also. Wolfgang, who has I think the next talk, will also present some results using bistatic systems with a cell phone base station as an illuminer of opportunity, which works at 1.8 gigahertz. So then there was an idea from the Americans to use a couple of satellites, called microsatellites. Here you can see the 6 satellites, which acts in a cluster, and combining the signals from each node, there should be a possibility to calculate that the image or what you get is like from a huge, very huge satellite. Unfortunately, due to financial constraints, this project has to be skipped in, always getting in trouble, 2003 or 2005. But doesn't matter, then the German was approaching on the horizon and put on a Terrasar satellite, which is working at the X-band, and in 2010 they launched a second one, which is similar to the first one, and they are working now coherently in space. There's not a bunch of satellites, only 2, but now it's possible to make coherent signal imaging with 2 coherently working satellites. The advantage of this constellation is that you will get a 3-dimensional map of the Earth instantaneously with a single flight of the system with a very high accuracy. Radar network, this is, can be seen in automotive business to save money. We have over-the-horizon radar in Australia, which has surveillance area of approximately 37,000 square kilometers. The official range is approximately 3,000 kilometers, which depends strongly on the atmospheric conditions. And the range goes up to and including the Korean Peninsula. Air surveillance with passive radar is a topic at our institute. There's a passive system, so you are only spending the receiver and you are taking the transmitter which is there, and they have chosen to take a radio or television transmitter as an illuminator, and they have the possibility to detect low-flying targets with very low radar cross-sections, and experiments were carried out, and it looks like that the digital audio broadcast systems shows promising results. A couple of experiments were carried out, and you will see it was validated in a NATO campaign. So working with NATO in RTO, what is a task group, you are able to get in touch with other colleagues from different countries working on the same problem. You can share ideas, you can see what have they done and learn from them, go on campaign with them, so you are able to compare your system to their systems. You are able to have a nice setup, for instance, get from vessels or aircraft for detection. How does PCL work? Like same behavior like Shane Home has changed dramatically. You will receive a direct signal as a reference. If you're not able to determine the transmit waveform, you have to monitor the transmit waveform. This is mainly done by a direct signal. This direct signal is also traveling to the target of opportunity. Here energy will be reflected, hopefully also to your receiver node, and using the time difference between the direct signal and the echo, you are able to determine the position using a minimum of 3 signals, 3 transmitters. The position can be determined. The advantage of PCL is you have no radiation, low power consumption, that allows covered and non-provocative installation and operation, significantly reduces system vulnerability, and very interesting for the industry, if you are not radiating, you do not need any frequency license. So it's quite easy. You can just deploy it, use the frequency. You have not to go to the government and ask, oh, I would like to transmit some energy at X band. You get the answer, oh, not possible, as a violent area. And you can just use it. It's passive. That's listening. Is promising if you're using components of the cells, no moving parts, maybe easy to install and transport, depends on your design, small footprint. You are able to design it on a mobile platform so you can perform tests somewhere else. And also if you design it correctly, can run unattended and maybe manage remotely. Bistatic XAR is also a topic which is at our institute. We had experiments performed with the paired airborne systems, but now very promising also using a hybrid system as an illuminator Terra X, which is flying there at nearly 500 kilometers above surface. You can order some images, pictures from an area. This is here. You also have to know when it is. You know the time. You can use the signal for your receiver, which is hosted here on a airborne platform, and you can calculate a bistatic image. The advantage of a bistatic image is that the dynamic range in the urban area where a lot of trihedral effects exist is dramatically reduced. And I've seen an image which was very interesting, a bistatic XAR image performed from kinetic. There was a tree, single tree, surrounded by a plain area, and there was 2 shadows. You ask, why 2 shadows? No, it's quite easy. One shadow comes from the torch or from the illuminator. There's no energy behind the tree. But looking from a different way, there's also the tree. You do not receive any energy from a different angle. So separating them over a very broad angle, you will also see 2 angles, 2 shadows of any object. But going not so far separated, you will not really recognize these 2 shadows, like in this case. Also nice, that's what I'm working, Maronda's map. Maybe some Harry Potter fans are sitting here, they know what Maronda's map is. The idea is to use everywhere nowadays wireless LAN signals to use surveillance, to build up a surveillance area. Radar, you have a couple of transmitters which are always emitting a beacon signal with a repetition frequency of, for instance, 20 milliseconds or 100 milliseconds. You can select it at your base station, and collecting the data with a dedicated receiver, knowing the places where your transmitters are, you will be able to monitor the system, look through walls. So, I'm at the end of my talk, and I think I will see this picture never in Ankara. no rain here, no water. So, any questions? Must be a British picture. I don't know where it's from.
Thank you very much for your report. First, I want to explore a question about the PCR system.
Yes.
You talk about there is a similar specific radar about the TV and the radio signal processing.
Yes.
Is there any progress on the powerful stuff like the active radar system for the PCR?
There is ongoing. I think there's work done and also some campaigns made. I'm not sure if still the interest is so high in using these active systems. You have to contact Heiner Kuschel. He is doing the main work in passive radar at my department, and I know there were several campaigns performed using active radar. I think there was a campaign in Hungary, but it's not very promising as we have to look in the same direction and have electronic antenna beams to follow the transmitted signal. And you will have a very strong direct signal sometimes, so high that your system may blow up. That's a disadvantage. I will talk this or point out in my next presentation the direct signal. There's a big problem on passive radar. The attenuation of the direct signal is just over the baseline, so 1 over the baseline squared. For the echo, you have the distance to the target, and from target to the receiver, both distance squared, 1 over the distance squared, and further the radar cross section. Let's say for a small aircraft 10, 20, 50 square meters. So this leads to a very low echo signal strength. In a monostatic system, that's not a problem. You will have designed your system in the right way if you are using a transmit-receive switch. You transmit a short pulse, a very high pulse, wait a couple of times, and then open your receiver. Then the strong signal in the near field has vanished. You are just looking in the lower range where you expect your echo. But that's not possible for a bistatic or passive system. You not really know when the signal is emitting, except if you have a really good coherent network. Then you may be able to shut down your receiver side when the transmit side should arrive at your receive node. But then you have you're blind typical time. You're not able to receive or to see anything.
Okay, it's good for it's a solution for the connection with the active system to passive radar from the ground lines. Maybe we can make some similar half active radar with the passive system.
A lot of people are dealing with this problem by using high gain antennas for the receiver side and just having the transmitter in the back. So you are looking in this direction, have the transmitter, then you have also a similar monostatic setup, but you are able to reduce the direct signal dramatically. By minimum, if you're doing it the correct way, you should improve the systems by 30 dB, maybe even 40, 50 dB. Depends on how you put your antenna backside slope is. And then you have a small antenna pointing just into the direction of the transmitter, so you are able to determine the transmit time and have a reference signal for coherent signal processing. But you have to look, that's my opinion, it's a common way to overcome this problem. It will be definitely a problem to have a transmitter and receiver this side and want to see a target on this side. I think that's a very big problem.
Yeah, I think it's a good research subject for the passive radar.
Yes.
My second question about the network. We talk about multi-static network. And as we know, in the early progress of radar, there is a track network, 1 kilobit in the transmission. Later today, there is a plus network, about 100 kilobits. And what about the sensor network? If we use our active radars signals in the network, and if we fuse all the signals of these networks, can we build a multi-static radar or multi-sensor network?
That would be possible. Only problem I will come to is depends on how good you would like to fuse the data. Would you like to have an incoherent system? You can do it today. Would you like to do it in a coherent way to improve your systems? You will run into huge problems. As coherence, to maintain coherence over a very huge area, over different nodes, it's not so easy. Depends on how much coherence you need. You want a coherence for single pulse, it may work. But doing over a very long period to increase your Doppler resolution or moving target indication, the demands on synchronization, phase stability between each node increases. So one has to take this into account. But synchronization I will talk tomorrow, mention it.
I was wondering about the bistatic application for the resonant mode to excite the creeping waves. I assume it's very sensitive to the frequency. Do you expect them to use some type of wideband, like chirp waveform in the transmit? And the second question is about the multipath problems. What would it change instead of using monostatic to bistatic? Is there a big difference in multipath problems? Thank you.
In the bistatic system, you can use the same waveforms like for a monostatic system. No problem to use a higher bandwidth, different bandwidths. If I understand the question correct.
For the creeping wave.
For the creeping wave, yes.
Resonant modes, so it's not that sensitive to frequency then?
I'm not sure, I must say. I'm not the expert on the bistatic radar cross-section. Yes? One has to investigate it to see it. Again, I think the measurement I have shown, this picture from this stealth object, that's a result which has been performed by Heiner Puschel a couple of years ago. I will go and ask him about that problem. I'm not sure if they have investigated it dramatically. Still, very interesting would be to have a database for bistatic radar cross-section. But that's a lot of work to do. A lot of bistatic constellations are possible. Going around, target is flying high, and so a lot of possibilities to get or put into the database. And what was the other question?
Multipath problems.
Fun?
Multipath problems.
Multipath. Same behavior.
All right. Thank you.
Okay, if no other questions, I think